it again. Okay, sorry about that. Yeah, okay. And then while I'm here, let me actually share my screen. Okay, cool. So yeah, like I kind of mentioned, I mean, the quiz will be about E2, or at least as far as I've gathered, but well, we've said what there is to say about E2. Um, like, we've kind of gone through and talked about it. And what I think would be kind of, what might be, and I hope would be kind of helpful if we did it instead, is like just kind of step back and thought about what we've seen so far. Because we're hitting the point of the class where it's really about reactions. And well, you've learned a good few at this point, right? And from here on out, it's just going to be adding to that list of reactions, right? And the ones that you've learned now until now are pretty key. So I think it's will probably be helpful just to look at and think about what we've actually seen and learned, right? So this is, well, okay, yeah. So reactions until now, well, there's really been 6. We've learned, that is a C, not a 6, there we go. We've learned 6 reactions, okay? And well, in our case, they happen to be really broad classes of reactions, which means there's a lot to say for each of those 6. Soon enough, like in the coming few weeks, you'll be learning really specific reactions, ones that can do exact things that you want them to do. And for those, well, there might not be as much to say because, well, they're a lot more specific. But these aren't, so these are general. And so we get the pleasure of learning a whole lot to say about them. Before, you've talked about SN2, SN1, E2, E1. We started off at the very start with acid-base reactions. Okay. And there was even this point where they were like, oh yeah, these are acid-base reactions. This is a Gen Chem thing, you learn them, whatever. But there's a good amount to say here, right? In general, we had to learn the pKa's of things. Yeah, so the pKa's of things, we had to see like what hydrogens can we pull off, what things are basic, right? There's also Lewis acids and Lewis bases. Which are different, right? Remember, they don't just play with hydrogens, they do other stuff too. Not as super important, but there will be times when they do come up. But anyway, this is besides the point, right? Because we want to get to the stuff that matters. But I guess the idea is that these are still things that you'll always have to look out for, right? So much of organic chemistry is just moving hydrogens around, and acid-base reactions are all about that. That's really what they're about, right? Okay, well, we got to play with these, and then there were all these ranking questions that were like, oh, which are the best bases, which are the best acids, and there were all those, and it's terrible, right? But from there, we went on and we did free radicals, halogenation. Okay. And part of this was, well, we had to look at where they halogenate. Right? We had to look at the mechanism, which in this case really came down to thinking about the Hammond postulate. Right? And well, these were kind of the main 2 things, right?
Are we ever really going to use like chlorine again? Because I feel like we always use bromine because it's like goes to a specific spot.
Yeah, so yeah, you usually will just wind up using bromine. I can't think of. So yeah, every once in a while you'll see chlorine show up. And there are even some points where they're like, oh, you just use chlorine anyway. Like it, yes, chlorine is selective, but sometimes they'll just say like, yeah, use it anyway. But in general, the thing is, we care about bromine because it's useful, and you're never going to be they're never going to need you to be creative with your reagents, right? If bromine works, yeah, use bromine. It'll be fine and good. And yeah, and okay. Yeah, I mean, there might be some kind of rare times where they'll ask you to use like some other stuff. I can't remember with the quiz that you had about this if they did ask for it, but every once in a while they'll give you some compound, like they can give you something that looks like this with oxygens, and they'll say like, oh, use this for free radical halogenation. That's pretty rare. So in general, it'll be bromine. There is one more reaction, and it's the only other reaction that you'll learn, which uses, well, it's the only reaction that you'll really need to know, which uses free radicals, which is, and you certainly don't need to know this yet. But if you have like a double bond and you want to put a hydrogen and a bromine on it, and you want to put it on the end, then you use light to do it, and that is as opposed to just putting it here normally, and then you wind up getting the bromine here, right? This is something you'll see in a week, but this is like certainly not something that you need to know right now. And that one you also just typically do with bromine too. So yeah, it's usually just bromine. Cool. Let me stop my share for one moment because just this is super quick. Okay, and okay, cool. Yeah, I just had to change my audio settings. Okay, cool. Yeah, and somebody asked what problem set we'll be working on. So we'll be finishing up problems from the last one and then working on this week's. They're both on the canvas. So last week we didn't get through all the problems, but that's fine because there's not that much to say this week anyway. So we'll really just be doing problems kind of the whole way through. Okay. Anyway, the point that getting to here with free radical halogenation is that this really lets us do organic chemistry. Okay, and what do I mean by that? Well, if we have a hydrocarbon, if we just have an alkane, the only thing that we can do is free radical halogenate it. Okay, there are no other options. Yeah, I mean you could burn it, but that doesn't. There's no point in doing that. Yeah, this is the starting point, and unless there's a double bond or a triple bond or something else hanging off it that's not a carbon and a hydrogen, then this is it. Right, this is how we have to start, and this will carry until all the way till you're done with organic chemistry. Like at the end of Orgo 2, there will be questions, synthesis questions that start with just hydrocarbons, and you will have to use this fact. Okay. Well, and Okay, once we got there, anyway, then we could do SN1, or SN2 and SN1, and then E2 and E1. Okay, so we're here. And we could do all of these 4 different reaction classes, right? And we just learned about them. And I might even say, so I said there are 6 classes of reactions, right? So we had acid base, free radical, and then these 4. I might even like kind of cheat and mention there's almost a 7th that's hidden in here, which is that E1 is reversible. Right? So just as much as you can say, and remember that E1 is usually when we have, you know, an alcohol and we just put in a really concentrated sulfuric acid, right? So as much as we could say something like this, whoops, that's totally not what it is. There we go. Okay. As much as we could say this, you can certainly get a problem which might look like, I don't know, something else like this, right? And then if we put it in dilute sulfuric acid, well, it's going to put an alcohol on there, okay? And in particular, it's going to put the alcohol on whatever is more substituted as a carbon, okay? Yeah, and so in this case, we would get something that looks like this. All right. The reason being that we can write out the whole mechanism, right? And we know that we're going to get a hydrogen on this thing. And we're going to form whatever carbocation is more stable, which is on there, right? And then we're done.
Does it have to specify dilute, or can it just say H2SO4?
I haven't seen a situation where they don't specify it. I think they usually will.
Okay.
Yeah. Although, well, they always like to mix things up. So, yeah, it's possible that they wouldn't specify it. And there's really only one thing that you've learned how to do with H2SO4, apart from acid-base reactions, but that's not interesting because, well, with H2SO4, you're just pulling the hydrogen off and putting it back on. So they might not need to because this is kind of it. But really, the only way that this reaction is going to go forward and not have a substantial equilibrium part going backwards is if you make it really concentrated.
Okay.
Yeah.
Thank you.
If you're writing syntheses, for example, you should write concentrated and dilute. Yeah, that'll be important.
So with the dilute one, is there going to be an equilibrium formed? Like, is it going to go back and forth a lot?
Yeah, it'll also go back and forth. The thing is, there's so much water that it drives it towards in the forward direction.
Okay, got it. Thank you.
Yeah, because really this is like, we can write the reaction like this. And if there's so much of the water, then it really pushes it forward. That's the reason we use dilute. And it's also the reason we use concentrated here, because once we get this water, well, it starts with so little water that it's going to really want to make water at this end. Besides some energetic stuff with sulfuric acid, but besides the point.
In the second reaction, what's really pulling the hydrogen atom?
Oh, like what is grabbing the hydrogen?
Yeah.
So it is these electrons in the double bond. Yeah, so like the hydrogen will take the electrons from the double bond and it'll grab it from whichever of these 2 carbons is well, like would be the less favorable carbocation, I guess, right? So you wind up with the positive charge on whichever carbon is more stable in this way. Yeah, it's like, yeah, I mean, that's like the easier way to go about it. There's like a bit more complicated of a way of thinking about it, which is that, like, if you draw this thing, right, this whole double bond is kind of like in a cloud, right? So there's double bond, and it's in a cloud above and below, right? And so it's kind of polarized. So like this side is kind of more negative, and this side is kind of more positive. Just because the negative charges are kind of, or electrons are kind of happier to live around here than they are on the other side. But this is again kind of like besides the point. Well, I mean, it is the point, but it's like kind of extra complicated. And yeah. Okay. Cool. Anyway, so that goes through E1, right? And then E2, I mean, some kind of important stuff being that we need a strong base and a weak nucleophile. Right? And in general, we also want anti-paraplanar. Okay. I say in general, I say it for a reason. There's at the risk of introducing new confusion, and and if you're happy with it being anti-paraplanar, then tune out your ears for a moment. It's possible to do it when it's in a configuration called syn-periplanar, which is when they're both on the same side. We'll see an example of this later if we wind up getting to it or we have time. But in general, like the overwhelming majority of the time that it comes up, it's anti-periplanar. I just mentioned syn-periplanar because I mean, if there's a whole quiz about E2, I don't know what they could really wind up asking about. So there are a few questions which it comes up. So I'll show you what that's all about. Okay. And then, well, SN2 and SN1, we can fill in the details of that if you want, but well, we've kind of gotten a lot of exposure to these, right? So, I mean, we could say stuff about solvent, right? We could say whether we need strong or weak nucleophiles. And yeah, there's some stuff about leaving groups, I guess, and some extra stuff, right? And then I guess we could say like stability, right? Carbocation stability. Yeah. But well, elimination reactions are kind of going to be the useful and important one. That's especially the case because the next chapter that you'll be going through after this is just alkenes and alkene reactions. Like once you have a double bond, what do you actually do with it, right? We put all this work and effort into just talking about how we make double bonds, right? And that's when we get the payoff, which is that we get this whole set of reactions that we can use these for. Yeah. All right. I mean, kind of again, we've said so much of what there's to say about these reactions already. And so, I mean, I don't have much more review to talk about right now. And I'll I'll certainly have a whole like broader review and more practice problems like Thursday, and yeah, we'll work on those. Yeah, we'll have those ready then. But I mean, for now, we just have practice problems, so I guess we should just go through those, right? Unless there are any questions, and as always, I mean, you guys already have been. Feel free to interrupt and stop me.
Can you just like maybe as part of one of the problems talk about like you have a synthesis thing, and then like I guess like after you've like sort of made part of it, like maybe like some like sort of like ring will like come together that seems like there's a triangle ring that doesn't seem like it should happen. Like, can you talk about how you like know that you should make those kind of?
Yeah. Oh, so like
when they don't give you the product, then you have to know that like some like two little like arm things will come together to make a ring.
Yeah. Yeah. Okay. I mean, I'll see if there are any of the problems that do wind up talking about that. I'm not sure if they do. Yeah. So there are a few cases where we do have that, right? So I guess the biggest case where they would say something like that, I guess, yeah. So just for yeah. So the biggest way that I think this will happen is if you have like, let's say an alcohol or an amide, an amine on your thing, right? So so if you have like an alcohol or this is called a thiol, right? Or an amine, if you have like one of those, then you could probably do a ring closure. And so the way that this is going to happen is, so I think this will typically happen by SN2. At least that's what comes to mind when I've seen these sort of things show up before. But they probably don't have to. But anyway, so like an example that they may try to give, which I know I've seen something like this show up before, is if, let's say, and I'm trying to come up with a good example. Oh yeah, okay, this is a nasty question. I've had this before. Like I've gotten this question before, and it sucks. So let's say you have this compound, right? And well, there's two substituents, and they're going to have to specify whether they're cis or trans on the same side of the ring or on the opposite, right? So let's say they're cis, and that means that what we have is, let's say they're both facing up, because that's just easier. Okay. And now, well, what we want to draw is we want to put it into chair conformation. Well, okay. How about, let me set this up like a real problem, right? So this is optically pure, and we're going to put it in, yeah, sodium hydride, sure. Something that'll pull off that hydrogen. Okay. Again, I mean, I'm coming up with this one on the spot. So there are probably some better reagents. You might see sodium hydroxide used, because this OH here is fairly like acidic, right? The hydrogen will come off kind of easily. So, okay, let's say that we're here and we're given this, and the question asks, what do we get? Well, okay, we can go ahead and redraw this, right? So let's just put down a ring, and then we'll worry about everything right after. So, okay, I'm going to say, this carbon is right here. All right. We drew our ring, and now we have to start putting things on. Right. So that means the bromine is sticking up like that. Okay. And well, if we're going, let's see, around this way, that looks like going around this way. And so that means that the oxygen is on, whoops, I wanted blue. Here we go. Okay, so that means that this carbon corresponds to this one over here, the way that I've been drawing it. And so there's a hydrogen that's equatorial here, and then this OH is sticking up at the top. Okay, well, we've done the hard work, right? We're kind of ready. We're set. So now give it some OH minus, right? It's going to take that hydrogen and pluck it off. So now this is an O minus, and this is a bromine.
Wait, sorry, I have a question. Where do you get the OH from? Like as a
Oh, sorry, that should have been sodium hydride.
Oh.
Should have been an H minus. You're right. Yeah. Okay. And then, well, yeah, we get hydrogen gas that bubbles off. All right. And well, can we do anything?
I don't think so. Right?
Oh, yeah.
Wait, Adam,
Yeah.
would it be possible? Oh, actually, never mind. You don't have the right reacting materials. I was gonna say, like, could you do like an intramolecular SN2 where like the bromine is a leaving group and then you attack with, but the reaction conditions are not. Like the solvent and stuff.
So okay. I didn't specify solvent. You could assume this is an SN2 or polar aprotic solvent.
Okay.
Yeah, but the point that you mentioned is kind of exactly the point that I was getting at here, which is, yeah, you would want to do SN2 because this bromine's a nice leaving group. It'll come off pretty nicely, but you can't here, right? You could very well do a ring flip, right? And okay, right, and you take your time and be really careful about it, right? And so what you wind up getting is, okay, this guy over here flips up, right? And now this O minus is equatorial. Well, okay, you still can't do SN2, right? You can't do backside attack.
So like this
Can you
is
explain
why...
what you mean by that? By no backside attack?
Yeah, sure. And then there was another question. I'll get to that. So with SN2, remember, what we really want is for this O minus to, and it's attached to whatever else, right? And then there's this carbon, and we want it to come from here, from the opposite side of the bromine. But we can't do that. There's, like, if you were to build this molecule or kind of like look at these pictures, right? This O and this bromine are, there's no way for this oxygen to come like, let me use a different color so that it's not too complicated here, right? There's no way for this oxygen to come like around and then down here, because it's on the top, right? It would have to come from the bottom. And likewise, there's no way for this oxygen to come like from the bottom because again, it's on the top of the molecule. So in this case, there's no way for it to do this. Yeah. There was another question.
Um,
Oh, there's two more.
you can go ahead.
I was just curious about, I know sometimes like if you can have like protonation happen where the hydrogen will attach to an OH group and then the leaving group will be water. Why is that not a thing in this case?
Oh, okay. Yeah, so this is kind of like a general thing. And well, in general, and I mean, here we go. Okay. We'll get to the trans case, I promise. So in general, if you have acidic conditions, here we go. So if you have acidic conditions, then carbocations aren't allowed. Oh, sorry, carboanions. Okay. The reason being is that if you have a carboanion, a minus charge, it'll instantly get protonated because you have a bunch of hydrogens floating around, right? So you can't, you're like not allowed to draw carboanions, right? If you have basic conditions, well, then you can't have carbocations because it'll just pull one of the hydrogens off. Okay. Yeah, so carboanions and carbocations. Yeah, and this is just because if you're in acidic conditions and you have a carboanion, it'll instantly get protonated because there's just a bunch of acid floating around. If you're in basic conditions and there's a plus charge, well, it'll pull the base is going to pull the hydrogen off like right away. So this kind of goes in general. And so in this case, sodium hydride is super basic because it's just going to rip off a hydrogen. Right? And so that makes it really basic. So this whole thing overall has to be a really basic like solution. And that tells us that we're not going to protonate here at all. Yeah, none of this is going to get protonated. We're only ever going to have minus charges on this molecule. This is like something really useful to keep in mind. This is kind of like an important thing. Whenever you draw mechanisms, like this is kind of a huge thing. They'll dock plenty of points if you start drawing minus charges in acidic solutions and vice versa. Yeah. Any other thoughts?
I just wanted to like ask some questions to clarify cis and trans specific to, I guess, like cyclohexanes for reactions.
Mm-hmm.
So per my understanding, in the case of wanting to have intramolecular SN2, like with the problem we were just doing, even though we have single bonds and like typically you'd have free rotation, because you are dealing with cyclohexane, like you're kind of restrained to have trans in this case if you did want to do the backside attack. But that's just for this case, because for like elimination, you would want trans usually because of the anti-periplanar arrangement.
Yeah, so you're exactly right, and this is kind of where this is kind of the point I was getting to, which is, okay, well, if we have this thing be trans, and well, let me put this in a box over here so we know what we're dealing with. And then if we have trans, okay, and let's draw this thing out, right? So let's put the bromine up top. We'll do out the rest of the problem pretty quickly because, well, we've kind of seen what this is all about. Okay, let's draw a ring, right? And then we're going to say red is here, and then it goes here, right? Same thing as before. So this bromine is sticking up. Okay, and oh, there's the OH there, right? And I'm just going to put an O minus because we already know that that's going to happen. Right, this is when we add sodium hydride. Okay, well, cool. This is certainly not going to be a backside attack either in this case, right? But, well, we could redraw them, and I should technically be using these arrows. Yeah, and so we could redraw this ring, right? There goes the bromine, and there goes the O minus. Okay, there we go. Kick that bromine off. And from there, what we wind up getting is this. Okay. Yeah. So here we did form this ring. And last week I even mentioned that, let me do this in like purple. So I even mentioned that this thing here, so this thing is called an epoxide. And these are super useful, and like, I mean, you'll see plenty of them in pretty shortly, like in a week or so. And they let you do a ton of important reactions. They're also complicated and confusing, so that's a waiting, but these are super useful. Okay, so cool, we could form this, right? And now to get to your question, which is that, okay, in this case, we were doing SN2, or, well, nothing, right? No reaction, just an acid-base reaction. But in some sense, we could also do E2. But in this case, well, when we had this bromine and then O minus, I mean, remember that we have to pull a hydrogen not where the bromine is, but next to it, right? And so we can't pull off this hydrogen here. What could, I guess, happen instead of this, and maybe I'll use a different color again, right? So we can't have it go here. What I guess could happen is if we have another one of these, right? And then there's a hydrogen over here. Yeah, so you could do something like this. It's possible. In general, we like, oh, that was ugly. So we recover that alcohol, and then we also wind up getting something with a double bond over here. Yeah, so you could do something like this too, I guess. This, I guess it's worth saying, this will be slower. And the reason it is because it's bimolecular. So you need both molecules to line up in order to actually be able to do this. Like you need two to, you know, smack together in the right orientation. Whereas over here, right, this is just within the molecule. This will happen like right away because it's just part of the same molecule. They don't have to find each other. Yeah. And I guess usually it's usually we don't tend to think about these intermolecular reactions too much. We usually focus on these. But I mean, yeah, this is something that could happen too.
Thank you.
Okay. Yeah.
I have a quick question
Mhm.
about that one. So does the transform only work because it's anti-periplanar, like for backside attack?
So be careful with those two terms. So backside attack is like in general. So this is kind of a case where it's confusing, right? Because yes, these two are anti-periplanar. But so anti-periplanar is good for E2. And the reason is because it refers to things that are on the same molecule, right? So on the same molecule. Right. Whereas with backside attack, this is for SN2, and the distinction here is that well, we're going on the same carbon, but also just the fact that it's different molecules, right? So here we can have two different molecules doing this. And well, it's coming from the it's approaching the carbon where like your bromine or whatever leaving group is already on, right? So like right, so it approaches the leaving group carbon, right? So in this case, like I guess where I had drawn it up here. So this oxygen and bromine, they are anti-periplanar. Yeah, like that kind of like that refers to their orientation, I guess. But we're not doing an E2, I guess. We're doing a backside attack because the oxygen is approaching where that bromine is.
So in the cis form, it's just not approaching because they're not opposite?
Yeah. So the oxygen can't come in from behind the bromine, which is why we can't do SN2.
Oh, okay, I see.
Yeah.
Okay.
Yeah, this is a case where like terminology is easy to get mixed up. And it probably doesn't help that like, you know, I pulled this example out of like a hat, and there are probably better examples for this, or there might be more distinguishable cases between these two terms. Yeah. Okay.
So like is trans just in this case happens to be preferred for SN2, but like usually trans will always be preferred for E2? Is that true?
Well, It's hard to tell, right? It depends on what you're doing it with. In this case, this trans molecule is I mean, you could do SN2 on this one, and normally you can't. It's not like a general thing. For E2, it usually won't really matter because, well, if we just have our general E2 substituent, right? If we just have like, oh man, I'm really getting sloppy with the rings. Okay, here we go. If we just have the general E2 thing, right? Well, we have hydrogens everywhere around it, and so we could always just do a ring flip, and we're going to be able to do E2 regardless. Yeah, except in this case, in the case above, well, for example, for the cis one, ring flipping didn't help. It didn't matter, right? It didn't change it so that we could do SN2. In the trans case, we could do SN2 because we could get backside attack. But when we're doing E2, for example, in a case like this, well, there's just a bunch of hydrogens around, so it's not gonna matter. In other words, you could also say this molecule here doesn't have stereochemistry, so we could just ring flip. Okay.
Wait, so
Yeah.
I have a question about
Yep.
that. So when you were saying like when you just have like one actual like different atom, so like a bromine with surrounded by all hydrogens, you wouldn't have to do like a chair conformation or like Newman projection because you can just assume that one hydrogen will be anti-periplanar.
Yeah, in that case you can. Yeah, there's also you can get a problem also that looks like this, which is annoying and awful, right? For example, you could get a problem that looks like this. So I wrote D here, which is for deuterium, which is another form of hydrogen. It's just distinguishable, right? It's a hydrogen with a proton and a neutron, so it's like heavier, but it reacts exactly the same as hydrogen, right? So they can give problems like this, and well, we could draw the chair. So the bromine sticks up, right? And then this is exactly the same like structure as what we drew before, just now with a D instead of an OH, right? And so we could draw them like this. And if we wanted to do E2 on this structure, right? Well, okay, we have to draw it so things are anti-periplanar. So that means we're gonna have to do a ring flip, right? And I drew it this way, so I gotta draw it flipped in the middle. There we go. Okay, so the bromine's sticking up, and then the hydrogen is sticking down. The deuterium is up. Okay, now if we want to do E2, right? Now if we give it, good base for E2, weak nucleophile, sodium hydroxide is a good one. Okay. Now if we do this, then we will wind up with, well, we're going to pull this off. It's going to go up here. Let me do this in a different color. Right. So this is going to come here, go up here, and the bromine's going to come off, right? And so what we'll wind up with is, well, I can't really draw a chair conformation for this one because there's a double bond in it. But we leave behind the deuterium, okay, and we keep this hydrogen over here.
Thank you.
Yeah. And then I guess it's also worth saying we could take that hydrogen off too, the one that's back there, right? And so we get a second product, which looks like, whoops, okay, totally running out of room here. Yeah, so we also get this thing over here as a product. let's see, what do we get? Okay, well, we could also, let's see. Oops, I want blue. So we can go here, kick this off and kick off this bromine, right? And well, that means we have a double bond here, right? And then we need to keep stereochemistry on this deuterium, okay? Because we didn't touch this carbon over here, so it retains its stereochemistry. And look, this is a chiral center.
So you're saying you can't treat deuterium like hydrogen. So like, for example, if it did happen to be anti-periplanar to a bromine, you can't do the same thing you would if it was a hydrogen?
So you can.
Okay.
You're allowed to treat it. When it comes to reactions, you could treat it exactly like a hydrogen. It's just that it's a labeled hydrogen. Yeah.
Okay, thank you.
Yeah.
So just to like talk about the stereochem for this, so like if you originally start with optically pure, like the optically pure starting materials, your products would be like one without any chirality and one would be like chiral. So would this be like one optically pure and one like optically inactive, or like how would you like designate it?
Yeah, you're right. Yeah. One thing would be, I mean, this double bonded thing would be optically inactive, and then this thing over here would be optically pure. Yeah. Yeah, you're right.
Okay.
Yeah. Okay. Yeah, this is a good problem to go over. I mean, so it's worth saying, right? If they're giving a quiz just on E2, this is the sort of stuff that I think they'll ask about, because like, again, I mean, if they're just giving like straight chain, alkanes, then there's not that much interesting to say.
Sorry, what happened with that blue arrow? How did it go like across the ring for getting the bromine? Or did it not? Oh, you're using the ones behind on that side. It's not the ones in the front. Never mind. Okay.
Yeah.
Sorry.
Yeah, it's the difficulty of drawing 3D on a page, and also thinking of it on the spot, because so it goes to the hydrogen that's behind, that's on like the back of the page.
Yeah, I thought it was the front ones. I was wondering how that was happening. That makes sense.
Okay. Yeah. So this is the sort of thing that they might ask for and look for, and yeah, it's
Could you repeat which one is optically pure?
Yeah. So this one on the bottom here. So this is optically pure. This one is optically inactive.
I'm sorry. I've asked this question a lot, but like I still can't like quite comprehend. What does optically pure mean?
Yeah. Okay. Yeah. So, so in this case, and so if it's optically pure, then what that means is that we have, well, whoops. So we'll look at this compound that we just drew and we were working with, like as the example. So there are two enantiomers of this compound. So there's this one, and I said that this one's a chiral center, right? The way you could see that is because there are 4 different things on it, and well, let me put it this way. So there are 4 different things that are on this, right? So there's, each of these 4, right? And well, here's 1, here's 2, this is 3, and this is 4, and they're different because the 2 sides of the ring look different. So they count as 2 different substituents. Okay. So it's a chiral center, and well, we could draw the enantiomer too, which is just what we get from flipping any two of those substituents. Okay. And so optically pure, this means that we only have one of the two. Okay.
Is this the same as saying like enantiomerically pure?
Yes, same thing.
Oh, Adam, I have like one, like, I think that this might be kind of stupid, but like, if you're finding like the Zaitsev product, would you treat hydrogen and deuterium as like both the same substitution?
Mm-hmm. Yeah.
Okay.
Yeah. Yeah, you would. So the idea being chemically, they're exactly the same. They will react this. Yeah, unless you get, way you want to take a few more years of chemistry. They'll react exactly the same. You could treat them exactly the same. Just the deuterium is labeled, so we have to treat it as if it's distinct from hydrogen, which is the reason that, for example, this is a chiral center. Because, well, we have a label on this deuterium. This hydrogen is any old hydrogen, but this one we know is special. In a way to say it, that's like kind of, I don't know, kind of vague, but yeah, it'll react exactly the same, but just the fact that we have this specially labeled, it tells us something a bit different. Yeah.
Kind of with this theme, like optically pure versus enantiomerically pure thing. On like the last like quiz, there were like some things that had like two products, and it said both of the two products are enantiomerically pure. Does that mean that that whole reaction is optically pure in the products, or not?
I don't think so.
Okay.
So I guess just so that would come up whenever you have diastereomers, right? So there are a few chiral centers, and then you're only changing one of them, right? One of them stays fixed the whole time, and the other one is changing. Yeah, I guess optically pure only applies when you have a single diastereomer, a single enantiomer. I guess, yeah. Nobody's gonna especially dock you on that though. Yeah, the main point that you want to designate and that they'll actually be looking for is that you recognize which stereochemistries you get out at the end, right? So like I could bet that you don't even have to write optically pure. If you wrote like, we only get this enantiomer at the end of your reaction, they would still give you all the points, because like that's what you want to show, right? So the idea is, well, I guess getting caught up in the wording and the naming isn't going to be like a huge and super important deal, because as long as you show that you recognize which products you're getting out at the end, that's what counts. Yeah. Although, yeah, I think you're right. Like using optically pure really only applies if we have a single compound, and if we have two diastereomers, both of which have one chiral center that's pure, then you probably wouldn't call it optically pure. But yeah.
Could you repeat that again? So if we have like two diastereomers as the products, would they both be optically pure?
So individually, I guess yes, but when they're combined in the same place, optically pure doesn't really hold for when you're mixing things together. So in that case, you would preferably say enantiomerically pure for each of them. But it's there's a lot of detail. That's not going to be the focus for this, right? Like they're not going to particularly care like which thing you say. If you want, you could ditch the term optically pure, and you could always just use the term enantiomerically pure, and like never once use the word optically, and you'll be totally okay. This is a way to say it.
In terms of optically inactive, so would the conditions for that be either like it's achiral or a racemate? Is that true?
Yeah.
Okay.
Yeah.
Thank you.
Yeah. In general, well, I no. So if you get something that has a stereocenter out at the end, you should write racemic if it's racemic. If you get something that has no stereocenters, you should write that it's optically inactive. Yeah, because if you get a racemic mixture, both of the compounds that you get are optically active. They're just mixed together, so you get no effect. So you should write racemic in that case, and then you should write optically inactive if there's no chiral center. I should write these things down. Here, let me change what I wrote here. So instead we'll say enantiomerically pure, and I'll adopt that terminology. So enantiomerically pure is this. So I guess racemic is if we have both. Okay, and then lastly, so optically inactive is no chiral centers.
What if it's like a meso compound?
I knew you were going to ask. I think that would. I think yeah, if I remember correctly, meso compounds aren't optically active. Like they would fall under optically inactive, but just write meso.
So like I guess so is the definition then achiral, or is it like is there a difference between I guess like saying no chiral centers and meso compounds fall under that versus just saying achiral? Like is there some type of differentiation or?
No, I don't think so.
Okay.
Yeah.
Sorry, could you differentiate more between optically pure and enantiomerically pure?
Yeah, so yeah, so we can so enantiomerically pure, and yeah, and I believe this is the case, and it's you don't have to, certainly don't need to get caught up on this. And so optically pure is like if for example yeah, so if we have like a single chiral center, and only one of its enantiomers, right? And then enantiomerically pure would be more, I guess, more general. So if we have like yeah.
Wait, do you mean if we had multiple chiral centers and only one of it is enantiomeric, or if
Yeah, so I believe optically pure would be like if there's like a single thing in there.
Oh, a
Whereas
single thing. Okay.
Yeah. Enantiomerically pure then would refer to like if there are diastereomers, each so each diastereomer that we get out is like pure at some chiral centers, I guess. Yeah, so I guess, okay. I probably could have said all of this with like a single example, which is that like,
Before you do that, like when you say a single chiral center, do you mean a single like chiral molecule, or do you mean just a center?
just a center within the same molecule, the same structure. Yeah. So in this case, okay, here we go. This is optically pure, right? So this thing is optically pure, and then let's see, what's something with two chiral centers? Yeah, and I don't know, screw it. Let's put an alcohol there, right? Yeah, right. And so both of these, here we go. So both of these, I guess, would be enantiomerically pure, and the reason being is that these carbons here stay the same. Yeah. Yeah, I believe so. Although the safest bet, well, yeah, it would be safe to just write it for both. Okay, just do that, and you'll be safe and okay and fine. Yeah, this is the most reliable way. Or you could just write a note and say like, these are the only two compounds we get, or something, right? Like that would probably wouldn't be that bothered by that either. Yeah. This is not the most important thing. I promise. Although I see where the confusion's coming from, and so I like, you know, yeah, I get it. Yeah. Although, yeah, I wouldn't get too hung up on it. If you get multiple products, just write it for each of them, right underneath each of them, like enantiomerically pure or whatever. If you wrote optically pure, I don't think they're gonna get mad or dock you or whatever. It's yeah. Yeah, at least I believe this is the case, and this is the way that I've seen it used. There might be some really nuanced, tiny definition part of it that I have mixed up here, but again, it's yeah. I wouldn't get super caught up over it. Just if you know that these two are the only structures that you get at the end, just write enantiomerically pure for both of them, if you so choose. Yeah.
What if you only get one of those, like one of the diastereomers there? Would that be optically pure?
Yeah, probably. Yeah, I bet it would be. If you wrote optically pure, nobody would get on your case about it. If you wrote enantiomerically pure, it would, you know, same thing. Yeah, I don't think anybody will will bother you over that sort of a thing. Cool. Right. Will we do some problems? Yeah, okay. Let's make a new thing, nice long sheet of virtual paper to work on. Yeah. Oh, I said we were gonna look at last week's problems a little bit. Why don't we? Okay. Well, let's look at one of last week's problems, and then we'll think about the other ones after, or if at all. I don't know. Yeah. So we'll do one of last week's problems, and then we'll look back at screenshot. Here we go. And then we'll look at what we have for this week, and then if we have time, we'll go back where I'll just tell you about a couple extra problems that I think might be kind of helpful. Okay. Here we go. Let me copy it and move it like usual. Okay, here's a bunch of reactions, right? And it's just to predict the product. This is like a standard, classic. We're all used to this sort of thing. Okay, and okay, so this first problem, well, we could redraw it, right? If we have, let's say this thing here, right? And there's a bromine down here, and there's one over here. Okay, and well, let me fill in with the rest. Okay, so we have this kind of stuff over here. And maybe let me even try to do something extra fancy, because I kind of drew it in a spot where we don't have a lot of room, right? Oh my God, that's the first time I've successfully done that. I'm so happy. Okay, here we go. Yeah, oh, let me draw it over here. That's better. Okay. So, okay, we have this and we have sodium hydroxide, right? Okay. And so what type of reaction are we going to do?
E2. E2.
Yeah, we're going to do E2. Okay, exactly. And well, now the question is, which of these two bromines are we gonna take off? Why don't I even say we give it one equivalent of sodium hydroxide, right? Which, well, they kind of threw at you at the last quiz and didn't actually explain what that meant. So we only expect to pull off one hydrogen. We only expect to do this reaction one time. We're giving it just enough so that it happens once and then no more. Okay. So let's say if I label these two bromines with red and blue, which of these two do you think will take off?
Blue, because it's the 3 thing.
Would it be the red one?
Yeah, because it's not at the bridgehead.
Yeah.
Yeah. So that is right. Yeah. So in this case, the fact that this bromine, the blue one, is at the bridgehead means that we can't make a double bond there, right? Let's say we were, right? If we were to try to do that, then what we would get would look like something like this, right? And okay, whatever, there's an extra bromine here, it doesn't matter. But the thing is that, well, there was that thing that's called Brett's rule, right? And it's especially specific, but the idea is that you can only have a double bond at the bridgehead if one of the rings in this whole system, right? And look, there's 3 rings, right? we have, so that's one ring. Oh, that's super ugly when it's not drawn with the rest of it, right? But that's another ring. And then we also have the flat one. Right, so we also have this. So this ring has 5, this ring has 5, and this one has 6. And Brett's rule says that we can only have a double bond at the bridgehead if one of these has 8 carbons, at least 8 carbons. Okay. And so we can't do this. All right. Here we go. So that means we got to take a hydrogen off around the red one, right? And there's a hydrogen here, but we can't take that one off because that would put a double bond at the bridgehead again. So we've got to take a hydrogen off from over here. When we do, well, oops. There we go. Let me actually draw this connected. That's what we get.
Real quick, what would it look like if one of the rings had 8 carbons?
In that case, we would get like 2 products, right? So let's say that we just went down here and what if we had that happen? Well, let's see, where am I? Okay, here we go. So what if it had an 8 carbon ring? Well, there's a couple ways that we could extend the ring, but why don't I just do this one? So now we have, okay, if we want to count, we have 1, 2, 3, 4, 5, 6, 7. Oh man. Okay. We gotta extend. This is why counting carbons is really important. Always count carbons, because, yeah. So okay. Let's say it looked like that. There we go. Okay. And so let's say that there was a bromine here and one on here. This is a single bond, by the way. There we go. Okay. Right. And so we could pull a hydrogen off here and here and here and here and here. Okay, there's going to be a lot of products in this case. Right? There's a lot of places that we could pull hydrogens off, and we could do it for either of these bromines. So well, let me just finish numbering my carbons so that I know that they're all good.
So Adam, like about like pulling off the hydrogens, do we just like, is it safe to assume because there are 2 hydrogens at like each of the points, there's gonna be one that's again anti-periplanar configure or conformation?
Yeah. In this case, yeah. This is okay. And I'll try to mention this without like going on a crazy long tangent. So there's actually a problem. Okay. Well, I'll answer the question in a second. So in this case, like, well, we could pull off a bunch of hydrogens, right? So we can do, for example, right? So we could do, let's see. Oh, you know what I can even do? Here we go. We're gonna really achieve speed. So why don't I just take this thing and then copy and paste it a whole bunch. Look at that. All right. I don't know what I just did, but Okay, all right, whatever. Well, I got two out of the way, so I'll take it. Okay, well, we can have a double bond form over here, right? And then we still have this bromine. And then we can have a double bond form over here, and we still have this bromine. And then plus 2 more when we get rid of the other bromines. Okay. For the original question, yeah, so in the chat we also have, you know, is it anti-periplanar or syn-periplanar? So let me answer this question by pulling up an example from, well, it's from a different textbook, but that's okay. I can do that. Here we go. Insert as a new layer. Where'd it go? Yeah, okay. Here it is. Yeah. So this first problem happens to have a lot to it, or a ton to say about it. So let's go into here. Okay. And well, so this is from a different textbook. But I'm telling you, I was really reaching to find problems, and well, this is one that I could certainly see showing up. Although it gets a little bit complicated, but it's worthwhile to explain what's actually going on. Yeah. So, okay, what is the question? Well, it says that we have the following mechanism. So it's basically the same, really similar question to before, right? Now we're just focusing on this bromine, which is fine anyway, because we didn't really care about the other one that much anyway. Okay. And now we have a deuterium here, so it's labeled, so we can actually tell what's happening. And what they say is, at the end, we wind up with these 2 hydrogens coming off. Or we wind up with the 2 hydrogens remaining, and the deuterium gets pulled off. Okay? Even though the deuterium is right next to the bromine, there's no way you can get the deuterium to be anti-periplanar in this case. Right? So instead, so this is syn-periplanar. Okay, and now we have to think about, you know, why do we do anti-periplanar or syn-periplanar in the first place? Like, what is the reason that even happens? Okay. The point is, well, so this is syn-periplanar E2. Okay, let's just say that. Okay, happens at a somewhat slow rate, given that the indicated product is by an E2 mechanism. Explain why the product forms. Okay, so it's syn-periplanar E2. That's why the product forms, right? How does syn-periplanar E2 happen? Like, where does that come from? So the idea is that when we have these 2 things opposite, right, what we're able to do, remember that when we form a double bond, we have these pi orbitals, right? And they're sticking up and down, and like going this way, right? The idea is that when we have anti-periplanar, this sets those orbitals up really nicely, right? Because, well, this thing is kind of already, these electrons are kind of already in place to float around here, right? And, well, yeah, okay. When we have, for example, these 2 things being, you know, not directly opposite to each other, well, then we have to take these electrons and we have to kind of like rotate them. They have to go, you know, they'll have to go like backwards into the page, for example, in order to fill that whole orbital. Okay, this is kind of like complicated, a bit high level, but this is kind of the point, right? This is why this doesn't really happen. because doing that takes a lot of work and effort. Now the question is, okay, well, why can't we just do that with SYN, right? Why can't we just have them both up at the top? Okay, and these electrons could just go and fill this space. It's pretty easy, right? They're already lined up for them to go into that orbital. They're in the right spot. The reason that this doesn't happen is because, well, this requires these two so it requires these two to be eclipsed. Okay, so remember, staggered conformation is always going to be better than eclipsed, remember? This goes back to Newman projections. So these two will be bumping into each other in this case. So this is like a hard setup to achieve. This normally just doesn't happen. That's why we don't do it as often, or we really pretty much never do. Right? In this case, these two are, well, they're staggered, right? So we, this is a nice conformation. This is something that we like to be in. This is much better. But over here, it's eclipsed. Right. In both of these cases, though, the hydrogen and the bromine are lined up like 180 degrees or 0 degrees. Right? They're both all along the same line, the same axis, if you want. So, okay, what happens? So in this case, in the case of this problem, this molecule is locked, right? It can't really, there's no wiggle room. There's no way to get the bromine and the hydrogen down here to be on this in the same place, right? So this bromine and this hydrogen, so we can't get them to be anti. Okay. There's just not enough wiggle room for that to happen. So instead, we've got to, I mean, it sucks to do it, but we have to do a SYN E2 instead. Okay. So we have to take off the deuterium. Okay. This is what happens in this problem, in this case. Okay. So that answers the question, hopefully. This is a sort of thing that maybe they'll ask on the quiz. I don't know if they would, but this is like, it's possible it exists, but it's kind of hard and complicated to do.
So going off of what Rebecca asked in the chat, so should we always try to rotate it to see if like anti-periplanar is possible for every E2?
Yeah. This is the reason I was really hesitant to bring this to mention and talk about this problem in the first place, because I don't mean to suggest that this is something that's like common or that happens often. Like, you will always want to get things to be anti-periplanar, like pretty much always. It's just in this kind of rare case that, well, they might tell you that this happens. Yeah, and I imagine that if they gave a problem like this, they might give you the product and say, like, explain why it happens, in which case this is it. This is the explanation.
In this case, the reason why it's locked is because of the bridge, or what is it?
Yeah. If you were, for example, to try to take this if you were to try to take, how do they draw it? They drew it like this. Okay. Yeah, if you were to try to draw this thing so that like this hydrogen and the bromine were opposite, you would have to put, well, let's see. You'd have to put the bromine and then this hydrogen sticking down. Right, you'd have to put it like that, and then, well, okay, so now this thing has to face downward and this one has to face upward, right? Yeah, except somehow this has to go up and this, yeah, this doesn't, like you can't really bend the molecule in the right way to do that. It's hard for me to be able to draw it. Yeah, this might be like one of those situations where you could try it with like your modeling kit, and what you'll see is that if you try to get this hydrogen and this bromine to be opposite to each other, either it'll take a lot of effort or like you'll break your modeling kit. Yeah, this is kind of one of those situations where it's hard to draw and see. And fortunately, that's why this problem kind of tells you what happens and they ask you to explain it instead of predicting.
So if you had to explain it in like a sentence, like if you were answering the question, how exactly would you word it?
Yeah, so how would I word it? Yeah, that's an important question, right? So it gives the indicator product by an E2 mechanism. So let's say, explain why the product forms. So the product forms by E2 using syn periplanar. The syn periplanar deuterium. I don't know, which is uncommon. Because syn requires it to be eclipsed, but the molecule doesn't permit anti-periplanar hydrogen. Yeah. Yeah, long sentence, I guess, and it's a dense one and it's complicated. But this is how I might say it in one kind of sentence. You could say something along the lines of it being conformationally locked too. Yeah.
Adam, can we go back to like B and C of like problem 5?
Yeah, we can. Haven't gotten through a lot of problems, huh? Okay. Yeah, so there are these problems, and this is like a mechanism that we, oh, it's not letting me draw, that's unfortunate. Okay, there we go. Yeah, this is a mechanism and a type of reaction that we haven't talked about and focused very much. Yeah, have you seen this type of problem, this reaction show up?
I just wasn't sure what it would be because I know iodine is a weak base. I like didn't think it would be E2.
Yeah, so there's so this is like a special reaction that happens. So if you have potassium iodide and you have bromines that are anti-periplanar, then you could do E2. on both of the bromines. Like you can take off one of the bromines, like this I minus will take off one of the bromines, and then it'll kick this over here, and then it'll kick this off. Okay. And so in this case, you'll wind up getting, whoops, that's not it. So you'll get something like this, right? And in this case, you can't get them anti-periplanar. Yeah. This is like a special reaction. It's a different one. It's another like form of E2, but it only applies if you have two bromines next to each other. Kind of specific.
Is that only with iodide as the base, or does it work with multiple? Okay, thank you.
It's just with iodine. It's yeah, it's kind of a specific one, and it's one that isn't really covered in the course. So it's like, I mean, yes, it's on this worksheet, and they probably won't ask about this sort of thing on like the quiz, for example.
Would C be syn periplanar?
C be syn periplanar.
Is it no reaction?
Yeah, it's no reaction. This is one of these like things where this is why I'm hesitant to bring up syn periplanar in the first place. Just because like it really like you should never see a reaction like this and think like, oh, I could do syn periplanar. Like don't think that. They'll probably tell you if it's syn periplanar. Yeah.
So if it's syn, just assume it doesn't work unless they tell you otherwise.
Yeah, I think that would be a safe bet. Yeah, I do think they'll tell you otherwise. There's one reaction that happens way down the course. Yeah, there's one other reaction where you get some really weird, like strange conformational stuff happening, and I think that one might have to do with like SN2 or something that happens way down the line, and it's kind of related to this, but I'll be surprised if they even mention it. And syn periplanar is like kind of that level of specific. It's not the sort of thing that you should think about very much often.
In the answer sheet, it says that there is a alkene product for C.
Like, could it react with another hydrogen on the carbon, like to the left of the bromine?
So this will only happen because potassium iodide is a really weak base. So this will only happen
if the bromine is anti-periplanar.
Yeah.
Okay, got it.
Yeah, let me see. So again, this is like not the sort of thing that's super like common or will probably show up like at all. There is okay, apparently oh, okay. So apparently you can get a reaction here, and this is like okay, I'm like checking the answer because I like this is not something that really comes up. So you can't get a reaction because it's anti-periplanar, but what you can do is you could just do like SN2, for example, right? And so so you do SN2, but to do that you need a ring flip. So you do a ring flip, right? And so what happens is you could draw the structure like this again, except now they're both here. Okay, and now you do potassium iodide, and you do SN2. And so one of these two inverts, right? And if you have like excess potassium iodide, and whenever they say excess of something, that means you have a whole bunch of it, so you can do the reaction a couple times, or you could use it a couple of times. Well, from there, you could use potassium iodide, and then you could, these now are anti-periplanar, and then you could do the reaction. And so now you get a trans double bond here like that.
How do you know that with the ring flip you'll be able to do a substitution reaction?
So you could do the ring flip or the SN2 in either order. You could swap the order of these two and it wouldn't make a difference. Yeah. The idea being that even if you did SN2 over here, it would still be, sorry, if you did SN2 over here, they would still both be equatorial as opposed to axial. And so you'd have to move them over to get them axial.
Oh, okay, thank you.
Yeah.
How do you do a ring flip with a molecule like this? I'm just a little confused.
So the way that I would do it is just pretend that there's a bond there. So you could just act like there's a bond there and treat it that way. And then if you ring flip one side, then you correspondingly ring flip the other. I guess that's complicated though, right? Yeah. That's kind of hard to explain and do. Yeah. So I would say, yeah. Again, I'll say, like, I don't think that this, I know when I took the course, they didn't talk about this reaction at all with potassium iodide and two halogens next to each other. I don't think you need to know this. I wouldn't expect them to ask about this. So yes, this is a problem on this worksheet, but I wouldn't worry about it too much.
Really quickly, with
Yep.
this problem, could you also have a cis double bond, or is it different because it's fused rings, so it's not considered to be like 8 or more carbons?
So you wind up getting a trans double bond specifically in this case because if you want to make the structure like this way, then if you want to have these things be anti-periplanar, then you need the hydrogens to be facing one inward and one outward in terms of the ring. This might just be a situation where building, well, in fact, this would really be a situation where building the modeling kit, building the model is actually like helpful and useful and important. But again, I wouldn't certainly not expect this to show up as the problem. Maybe they would ask about something with like a 10 carbon ring like this, which looks like 2 rings, although it's not fused, right? It's not bridged in the middle here. We just pretend it is because it makes it simpler to think about. Yeah.
Okay. Thank you.
Yeah. Okay. Here we go, and these are now like the more interesting and relevant problems. Okay, well, if we have sulfuric acid here, and well, we could even say it's concentrated. They didn't say it's concentrated, but if we're heating it, that means we have to put some real strong conditions into this reaction. So we're going to treat it as concentrated too. Okay. In this case, this is one case where they didn't specify, but well, yeah, it's helpful to. Well, yeah, they didn't specify, but there's like one thing that we can do here, and it's kind of clear what that one thing is. So we're gonna do it, right? Okay. So we protonate, and then somebody tell me what happens.
The bond move in the square to make like out one.
Yeah, right. So okay, these are equilibrium, right? This is still equilibrium. Okay. This is not equilibrium here, right? We take this whole thing and we shift it over to here, right? And remember, if we're counting carbons, right? So this is So this is 1, 2, 3, 4, and 5, right? And then this is 1, 2, 3, 4, and 5. Because carbon 2 lost its bond. Carbon 2 lost a bond. So now carbon 2 has the positive charge. And then, okay, we finish off the rest of, we finish off E1 by pulling a hydrogen off somewhere. So we get a double bond. Okay. In this case, all right, well, we kind of go through the steps of the process, right? We have the ring that looks like this, right? Yeah, it looks like this. This is a really ugly ring. I'm sorry. Okay, and then we don't get a ring expansion in this case. Why don't we?
Is it happy with 6?
Yeah. In general, it's really hard to make 7 and 8 membered rings. Yeah, it's hard to do that. So we just make this product. That's it. Okay.
Wouldn't you get another product though? Like you would put the carbocation like it would in the one that's like a tertiary. Sorry, like you would have the plus sign in the tertiary carbon.
Okay. Yeah, you're totally right. Yeah, I was getting way ahead of myself and not thinking about all the, extra rearrangements that can happen. Yes, there's a hydrogen over here, right? And so we can move this whole big hydrogen. We take this whole thing and just move it over, right? So now this is a forward arrow, no equilibrium. Okay. And that's a much better carbocation. And so this gives us as products, well, we can get this plus we can get a little bit of this guy here too. Okay.
What do you call the left one major though?
Yeah. In fact, I would. Cool. Nice. We did last week's worksheet. And it's almost 1 p.m. Okay. Yeah, so we have more from this week. We have a workshop on Thursday as well, so you might be able to make that again. So it's on the worksheet for this week, and I'll put the solutions up after this too. They're on the Canvas. The workshop Canvas, which is separate from the course Canvas. If you're not on that, do let me know. I think we will kind of wrap it up there because we kind of talked about the things that we needed to do. Somebody actually reminded me in the chat, which is very helpful. Yeah, I there's normally a sign-in thing, and I totally forgot to make a form for it. So what would be just extra easy if it would be just probably easier for all of us for me to not have to make a form right now, because that would just be complicated. Just send your pen ID number in the chat, DM it to me. Don't send it to everybody. So for example, right, it's the 8-digit number thing, right? So for example, mine is well, I don't know what mine is, but it's this is example 1, 2, 3, 4, 5, 6, 7, 8. There we go, right? Yeah, just send that. It's again, I'm not stealing your identity, I promise. Oh, I just DM'd it to someone. Whoops. Example. Yeah, there we go. Just send that. Oh, I just DM'd it to someone too. Oh no, it's because everybody keeps DMing me, and oh my god, oh, it's a mess. Yeah, just okay. I think it's fine. Yeah, the benefit of having a chat feature. When we did this in person, there would be one sheet of paper, and everybody would just have to go and write their name on the sheet of paper, and there would be this big line or whatever. And yeah, and then afterwards I have to go and copy them all down, and oh man, what a mess. Chats, the benefit of the chat feature, everybody can just type it in at once, right? Really got to look at the bright side of having virtual learning, right? Yeah. Yep. Okay. Cool. Yeah. That is it. That we'll talk about the other problems next workshop. Maybe next workshop we'll really just go like grind through some practice problems, like a whole bunch of them, including the ones we were supposed to do this week. Oops. Yeah, I think we got a lot of review in though, and I mean that's what I tend to have most of the time anyway. So hopefully you found that helpful. Besides just going through countless practice problems. Yeah. Okay. Any questions? No?
Sylvia actually has a question about physics 280, but that's not...
ask it in a moment. Anything? No? Okay. In that case, see you all